Now you may be familiar with these devices, voltmeters or multimeters. They are designed to measure relatively large voltages, and they react very slowly compared to oscilloscopes. This oscilloscope is capable of measuring voltage differences down to 10 thousandths of a volt and time differences down to 10 millionths of a second. To get an idea of why you want to measure these very tiny voltages and very short time frames, imagine you have a fan like this which has a little electric motor in it. You spin it around, that motor is spinning so fast that the small changes in electricity are extremely difficult to see. Okay. Similarly, again, electric motor, say in this car, in this toy car, the electric motor is spinning so fast that it's actually difficult to see what's going on. Okay. Why would you want to see those little differences? It turns out that, well, when an electric motor is spinning, that means magnets and coils, wires, pieces of metal and everything are sort of interacting with each other, and that generates waveforms, waveshapes. And those can tell you things about how the motor is working, or more particularly, how it's broken or not working. Similarly, we have at a larger scale, real big electric motors, same kind of thing. Also things like, for instance, the fuel injectors in a real car. These are devices where magnets move pieces of metal. An oscilloscope can show you the little tiny voltages the way they're supposed to be in the fuel injector. And if they're not like that, then you have an idea that the thing is broken. So I'm going to proceed by going through toys, through some examples of these things to give you an idea how to use the oscilloscope. Now, similarly, the sounds coming out of earbuds or speakers in general are, of course, occurring very rapidly. An oscilloscope can get a look at what's going on with the electricity that's generating those sounds. So if there's something wrong with your speaker, you can tell. Similarly, if you've got the insides of a microphone, then you can attach it to your oscilloscope and also get an idea of what's happening to the electricity inside here. So if things are broken in the sound world, you can get some idea because the oscilloscope is fast enough to show it. This video is a little different than normal videos that I make. It has very little to do with seismic units, although there is some relationship to sound waves. I'm going to show this little oscilloscope and how to work it. You can see a mock-up of it over here, so we'll start with that. First thing to turn it on, press this yellow button over here for 2 or 3 seconds. The next thing to remember is don't touch this auto button. You'll have to wait 30 seconds. It won't do you any good. It'll just be confusing. Okay. Now, the real button you want to worry about is this toggle up here at the top. As you toggle it, you'll find that these parameters highlight in blue across, including this marker arrow and this little arrow. When a parameter is highlighted in blue, it means that you can change it using these up and down arrows over here. And that applies to any parameter in blue. You press these, something will happen. Now, because we're dealing with batteries, you might think that we're going to have this option to be DC, but usually it's going to be AC. Also, the time will be shortened to something like 1 millisecond, 2 or 5 milliseconds, something like that, and or 10 millivolts or 20 millivolts or something in that nature. Now, when we use the toggle to highlight the voltage scale over here, then these buttons will stretch and compress the image over here like this. So it'll change the scale of the voltage. Now, when we use the toggle to highlight this parameter, this is the time scale. It will therefore stretch and compress the image this way. The time will be stretched and compressed this way. When we use the toggle to make this arrow blue, then these up and down arrows will move the entire image up and with the blue arrow over here. Okay. This in fact is the 0 voltage reference point. Or officially, it's the 0 voltage reference point for channel number 1. If you look closely, you'll see a little 1 in here. More sophisticated oscilloscopes have more than one channel, so you'll find 2 or 3 or 4 channel markers on here, all of which are the 0 reference points for their particular tracing across the screen. Now, to see all that just using a battery, we want to connect this battery across the leads of the probe here. Fortunately, that's a little awkward. Looking around for a pair of wires to make that attachment, we see some red-green show. So we'll be able to use the handyman's secret weapon, duct tape. Having performed this amazing feat of engineering, we can now attach the leads quite easily to the wires. Having set the voltage and the time scale appropriately, we can now see the reaction quite easily as we touch the second lead. We've closed the connection. And toggling over, we can change the scale of the voltage. Like that. Moving the scale over to the time, we can now speed that up or slow it down. As we make the connections, you can see that. Now we've slowed down the time scale again, and now we've highlighted the blue, and now you can see that the image moves up and down on the screen. Again, as we change the 0 reference point, the blue arrow goes up and down, so does the 0 voltage point. Over here I have one of those little, the sunlight comes in the top, through the solar cell, charges the battery, and then at night the light comes out the bottom here and illuminates the walkway. You've seen them. Now I want to get the solar cell out of this. I can do that using a sophisticated technological device, which gets me the solar cell. As you can see, it's a solar, just a couple of wires sticking out. Everything else is gone. But now I've got a solar cell attached to the probe, and there's no battery in this configuration, of course. The solar cell is producing the electricity. You can see it as I cover it up. So the trace on the screen is changing according to how much light my hand lets into the solar cell.
Here is a common connector. Here, a needle is used to make a back connection. Here, 2 thin strips of metal are jammed into the battery connections. Similarly, 2 nails are jammed into the battery connections. With this kind of fan, you can simply connect the battery to the wires.
We're going to be dealing primarily with toys and things that are battery powered. So you might think that we're going to keep this parameter at DC, but no, I'm going to change it to AC. Similarly, you might think that we're going to keep the time scale so we can see it. Well, we're going to change that time scale right to 1 millisecond. And we're also going to change the voltage scale to 10 millivolts, or scales near that, depending on the battery and the vehicle and the toy and whatever. What AC does is it simply eliminates any part of the DC. So the battery voltage, the 1.5 volts, will be subtracted. So as soon as you hook it up, you'll see just a flat line in the middle of your screen until you scale it for the voltage. Then you'll begin to see a bunch of. As the electric motor runs inside the toy, it's going to generate little voltages across the battery, back voltages to the battery. In order to see them, we have to increase these scales. Otherwise, all we'll see is this flat thing, because AC option subtracts the battery voltage. Or actually, it subtracts the average voltage, which of course for a battery is whatever it is. So for a battery, it's 1.5 or 9, whatever you got. Now, when you press the mode button, you'll see that the auto over here will change. You'll get a choice of normal or single, and then it'll rotate back to auto. If instead you press the mode button for 2 or 3 seconds, the direction of this arrow will reverse. Mode and all this over here has to do with triggering, selecting it, getting it blue. Using the up and down keys, we'll move this up and down. The oscilloscope will then be looking for that voltage over here. The first time it sees that voltage, it'll put it there. The oscilloscope will then wait a certain duration, and it will look again and put that there. I mean, think about it, the chance that a fancy waveform would exactly hit that edge all the time is very low. So it actually has to look for the voltage. Now what this arrow means is it's looking for the voltage increasing this way or decreasing this way on the waveform. So it's going to grab either something going up. So if this is up here, so it's going to be grabbing a waveform on the way up or on the way down. So if you so for instance, if this is up here at 2 volts, then it's going to look for 2 volts going upwards. And if you change that arrow, it's going to look for 2 volts going downwards. If you take the mode and you set it to normal, if it can't find that voltage up or down, it simply will show a blank screen, okay? Auto waits a certain amount of time and then shows whatever it's got. Single waits and then shows one waveform, and then it will stop. And with single, it will stop in order to start again. You hit run. The next time it finds that voltage, it'll stop. Hit run, and it'll stop. Now, no matter what mode you're in, you can press this button and it will stop, and it will freeze the image. So if you have things that are wandering across your screen and you can't get them to stop so you can see what's going on, if you press the run button, it will actually stop. You will get the wave shape will be just frozen or whatever it is at that instant. If you press the run button again, the stop will be removed and it'll keep going. To understand triggering a bit better, let's say that we had just this wave shape, and that was it. This yellow line continued that way forever, and it continued. This yellow line continued this way forever. Now, the reason when it triggered, because of this voltage level here, and the fact that it's going upwards in this arrow, then as soon as it went above that little voltage in the upward direction, the oscilloscope would capture this image, would pause at this image, okay? But what would happen if we moved the trigger voltage up to here? If we moved the trigger voltage up to here, then the oscilloscope would start right here as the voltage increased beyond the trigger point. We would then only have a fraction of the image, and we would get a long tail of flash, of course, because we have the arrow upward, so it's a positive increase in the voltage. If we press the mode button for 2 or 3 seconds, it will flip this arrow. That means that it will be looking for a voltage decrease. but it's the same voltage value on the trigger arm. So it's now looking for a downward slope of the voltage. Notice that in this case, we've cut off a lot of the wave shape. Now, more sophisticated oscilloscopes can, of course, trigger on better, more complex scenarios. You can specify the shape of the wave, and the oscilloscope will then look for that. That, of course, requires a lot of complex computations, which this one can't do. Now, of course, in many cases, the wave shapes repeat. Electric motors, for instance, will make the same wave shape again and again as it rotates, or at least very similar wave shapes. Now, in some situations for this oscilloscope, you may be able to sort of freeze it at the front half of the wave shape and look at that, and then trigger on something else and freeze it on the second half of the wave shape, and then you can sort of mentally combine those. Remember that if you just can't get it to stabilize, you can press this run button here, which will stop the image, and therefore you can have a better chance to look at it, and maybe that'll do the trick. Now, if you push the auto button that I told you not to push, the word auto will appear here. The scope will then run through the various voltages and time scales, and as well as AC/DC, to try to figure out to get you a nice image automatically, so that you don't have to manually adjust everything using the up-down arrows. The reason I didn't want you to press this is, of course, you needed to understand what was going on. And also, quite often, this doesn't really work out necessarily, depending on these weird things you're doing. Now, you may have some numbers on your screen. If you press the run button for a long time, 2 seconds, those should go off. Press it again for 2 seconds, they'll come back on. Okay, so you can toggle the numbers on your screen on and off. But the numbers are, if you look at them, maximum voltage, minimum voltage, average voltage, root mean square voltage, peak to peak voltage, frequency, duty cycle, and something called cyc. Cyc appears to be the period of your waveform. Okay, the time it takes for a waveform, one complete waveform to show. What duty cycle is, the percentage of the waveform that's above 0 compared to the entire waveform. So basically, when you turn a switch, how long is that switch on and how long is it off? So if it's on for 1 second and off for 9, you've got a duty cycle of 10%. They seem to be affected by the scale that you're at. So if your waveform is not actually being imaged, these numbers seem to all go bad. So it's kind of like it's actually looking at what you're seeing. So when things are off scale, pressing this run button for 2 seconds might not bring the numbers back or remove them. You have to sort of bring things into proper scale, and then the run button will, 2 seconds will toggle the numbers on and off. One thing you might want to do is simply take a microphone and hook it directly into your oscilloscope. No batteries, just hooked in. If you then tap the microphone, you'll see a wave shape of this nature, assuming you've set it up properly. Notice that I have it on single trigger and it's stopped. Okay, so that's how I captured a waveform. This microphone actually came out of the center of a Guitar Hero mic, which you may remember. I picked it up at the dollar store, honestly, just so I could do this demonstration. Now, I've actually taken a cheap speaker that makes sound, and I hooked it up the same way as I hooked up the microphone. No batteries, just a straight hook across. Then when I tapped it, I got this. Speakers and microphones are essentially the same thing. They're coils near magnets. One uses electricity to move something which produces sound, and the other uses sound to move a coil which produces electricity. One, of course, is designed more delicately. You'll notice that the voltage I had to set on the speaker is much higher, is much more delicate than for the microphone. That makes sense. It's not designed to work in the direction I'm working in, but it does. Okay, that's interesting, you say, but you don't happen to have a speaker. Well, actually you do. You've got two of them. Little earbuds like this, of course, exist. If you hook them up so that one's at the bottom of this connector and the other lead is at, say, the top, your oscilloscope will there be actually picking up the electric signals that are being generated by one or the other of these. So if you kind of tap both of them, the back of these, on the back of a counter, you can see this kind of wave shape. Things that aren't designed to be microphones are actually working in reverse, okay? Now you can, of course, do the same thing with headphones that you did with the little earbuds. Again, hook the probe across the connectors. There's no battery, then just tap, and you'll see some reactions on the screen, depending what. Now, of course, the way it's hooked, only one of the earpieces are really going to send any signal back down. If you connect the middle one instead of the end one, then the other headphone will show something. I'm wearing a red shirt. You know what that means? On Star Trek, it means don't beam down. It's dangerous. Now, you can see I'm wearing this red shirt. You know what that means? It's time for a safety lesson. Okay. So, now, in this video, we're going to be dealing only with low voltages and batteries, 9 volts, whatever. So, we're not going to have too much of a problem. You don't want to burn out your scope anyway, so you don't attach anything. But a word of warning here. You might think that getting a high voltage requires starting with a high voltage or fancy electronic doodads like this. But that's not true. A basic gasoline engine, the spark plug in those things, that's a 10,000 volts. And that's for a chainsaw or a lawnmower or anything like that. Your car, or most cars, gasoline-powered cars, they have a 12-volt battery. But somewhere in there, there's spark plugs. And those things are at about 20,000 volts. So now you think, well, cars, they got a lot of sophisticated jazz all inside it. And they got a lot of sophisticated components and diddlies and thingamabobbers to make all that voltage. But your chainsaw doesn't have any of that. So a chainsaw and a lawnmower are able to manufacture 10,000 volts using just a piece of wire and a magnet. So, and maybe even less than that. So, you know, a couple of thingy-bobbers and a doohickey, and you got 10,000 volts. So, be careful. Don't screw with things you don't understand. Don't screw with things you haven't done. Be damned careful. Okay, so in conclusion, simple is not the same as safe. Small is not the same as safe. You use a solar cell and the oscilloscope to measure the exact speed of a fan, like this one. Now, you'll notice this actually has 3 wires on it. 2 of them are the power wire. The other one is basically a tachometer. That is, it measures the speed and sends it to the central processing unit of your computer. We're not going to use that one. You just need to find the 2 power wires. You can put a 9-volt battery on this and it'll spin even though it's designed for 12 volts. So the question is, and what's it actually spinning at? Well, we'll be able to measure that using the oscilloscope and this. So how exactly can we use a solar cell to measure the speed of a rotating fan? Well, once more, we need to use the handyman's secret weapon, duct tape. So now I've duct taped off most of the solar cell except for one little part of it. If we take our fan and align it with that little part, and we have a light source coming from, say, the camera, then as it rotates, the fan will block the light going into the solar cell, that voltage will then appear on the oscilloscope. So as this rotates, the fans alternately block the light and allow it through. Thus, the oscilloscope will react and we'll be able to count that given its time scale. That doesn't sound too hard. One thing to see, however, is that this fan has 11 blades, whereas this fan only has 7 blades. So if you need to take that into consideration. Fan speeds are usually in revolutions per minute, RPM, whereas the scale of the oscilloscope is some sort of time scale. So we have to do a bit of arithmetic if we want to get the right answer. Now, you probably wanted me to show you the little calculations involved in computing the fan speed. Well, do it yourself. Get on with it. And clean your room. Now then, when you measured the speed of the fan using the solar cell and the oscilloscope, you may have got numbers like near 3,600 or 3,000. 3,600 in North America and the top half of South America, and 3,000 pretty much everywhere else. It's a hint that you may have done something wrong by making an assumption that isn't true, or at least ignoring something that might be true. Now, along with your scope, you may have also received a little probe, a little fancier probe that looks like this, okay, or something like this. It also comes with a little metallic piece that looks like this. This is an adapter necessary to hook it up to this particular scope. This little metallic piece goes into the coaxial end of the probe. So then you would then remove this and hook that in instead in its place. So then you'd have it. Now the other thing to notice right here, if you will, is that there is a small hole right there in the gray plastic end down at this end. This small hole actually goes with this little screwdriver. The little screwdriver goes in here and makes an adjustment, a calibration adjustment. And so we're going to show how to calibrate that. Calibration is actually necessary when this red button here, when this red switch is turned to 10x, that's when you need to calibrate. 10x here means it's attenuating, that is reducing the incoming voltage by a factor of 10. So 10x means 10 times smaller voltage. So the first thing is we want that switch on 10x, so a 10 times reduction. Of course, you'll notice that the probe actually has a ground connection like this. It also has a plastic part which you can push in and out, and the little metallic tip will show on the end here. The other probe had two simple alligator clips. This has got a little metallic one which you can show this way. The other thing that you can do is take this plastic component and simply pull it off, and you'll see that there's another tip right here. So now you have again the two ends, the ground end and the sort of the business end, the little metallic end. So put that back on, and there you go. Now to repeat with the mock-up, this end is kind of going over here, okay, plugging in over here, okay. And then the screwdriver is making an adjustment if it's on 10x. Now, the scope provides its own calibration signal, okay? And that's actually a little metallic piece right here, basically in the center. And so that you would have this end hooked over here, and then the end of the probe here would be in there, would touch that calibration. Not the ground, that doesn't matter here. It's already grounded. We put it in here like this. So this little part would hook in to the little the little sort of silvery metallic calibration thing in there. This little thing is actually manufacturing a square wave. So when you attach it like this, what's actually going on, that little thing is always manufacturing a square wave. So the scope is putting out a square wave onto that just for calibration purposes. But that's why it exists. It is a separate circuit having nothing to do with the rest of the oscilloscope. When you have adjusted all your parameters, you will see a nice square waves in here. And those square waves are manufactured to be perfectly square, or as close to perfect as you can get. But probes, of course, are made out of metal, and they have wires and capacitance and inductance inside them. And so you need to be able to make an adjustment. To make the calibration is to put the screwdriver in here and turn it back and forth while looking at square waves and then getting them to be perfectly square, as square as you can get. This probe, of course, is typically for little measurements on little circuit boards and little radios and little PCs and whatnots, not like the toys we've been dealing with. Now, you can use this with what we've been doing, the little toys and everything. It's just a question of what's more or less awkward. Now, when your probe has been adjusted to 10x, that's 10 times attenuation, 10 times reduction of the signal, either using this little red button, or there's separate things that actually hook in here, and we'll do that, 10 or 20x. What you need to do then is to use the toggle to change this to 10x to x10. When you change to 10x, nothing will happen to this. But those numbers that go onto the screen, well, they will then be adjusted by a factor of 10. That's right, that's all. That may seem kind of odd, but that's the way oscilloscopes developed. So that the oscilloscopes developed from actual physical tubes, cathode ray, that's electron gun tubes like early televisions, in which they had a beam that moved back and forth. So there's a certain amount of physical limitations caused some of these parameters to end up where they are. For instance, you might argue also that this trigger arrow here that says the voltage of the triggering, well, it's actually doing something that sort of appears on this side, so that's maybe backwards. But again, the physical limitations of the original electron tube required you to do things in a certain way. Similar with this grid. You might argue, well, the grid should be mobile, but it isn't. Well, remember, the original tube, if you wanted a grid, you had to actually draw it on the front of the tube. Here, sure, computers can draw grids on things, but didn't have that technology. So a lot of this stuff, the words like auto and normal and single, again, that all just evolved without any, so what they actually mean and why. Again, same thing with AC-DC. Well, oscilloscopes don't measure that. AC-DC is current, alternating current, direct current. Well, oscilloscopes don't measure current, not directly. So this word current here is misleading, but that's the way it is. Similar to the way the word trigger itself actually got into existence. The physical device actually had a beam of electrons which were pulled from left to right on the screen, and the trigger circuitry caused that beam to wait until it saw something, and then it would trigger the beam to go across. Now, it may occur to you right now that I'm just kind of wandering around looking for little things to try the oscilloscope with. You're right, that's about it. Toys and speakers and earbuds and little things like that. Yeah, little fans, all that kind of stuff. That's exactly what's going on. Try some yourself, but don't do anything dangerous. No hooking into anything that you don't understand. No playing with any fiery substances. No making big sparks. No tying into the circuitry of the house or anything else like that that has high voltages, or no spark plugs, nothing like that. I mean, after all, you can learn just as well with a toy as you can with a big motor. Now, along with connectors and earbuds and microphones, we're also going to be going online to tone generators that will make specific frequencies of sound. So we can get a look at those in the oscilloscope. Sound, sine waves, square waves, triangle waves, that sort of thing. And then we can see some combinations and what those things will look like on the oscilloscope. Online tone generators are similar to signal generators. But if you already have a signal generator, then you probably aren't watching this video. Conveniently, you can actually find sort of extension leads of this type which have the same connector on both ends. The reason that's useful is you can plug one end into your computer, your PC output, the phone output, so then you've got these to attach the oscilloscope to. Then when you hook this end to the PC, the sound will try to come out this end and you can see it on your oscilloscope. Now then, for this little earbud, I've actually cut off one of the ears, and then I bared the two wires that were coming out. There's actually two wires in here. It's a coaxial cable. I actually used a soldering iron to melt the outer light blue, then pulled the little metallic insulation, which is the outer conductor, away from that one, leaving me with a little black wire that had another conductor inside it. I then used the soldering iron again to melt the little black insulator off, and that's how I got this. Now you want to be able, the reason to do that is you need something to attach to the oscilloscope. If you don't have this sort of lead that has two ends on it, you can do it that way if you need to. It's actually tough to get to, or maybe you can cut off some wires here. The reason I'm saying all that is we're going to go to look at the online tone generators. Those things make waves of one type or another, sine waves, square waves, triangle waves. And so we want to be able to see them. With the earbuds, you could hook in one side and sort of listen on one side and then see it on the other side. With this kind of thing, well, you can just see it on the oscilloscope. Now, online tone generators are basically signal generators, simple signal generators. Make sine waves, square waves, triangle waves, things like that. One thing I didn't find was a spike generator. That is just a quick spike and that's all, or random spikes. Now, square waves have some properties that are similar to spikes and Dirac delta functions. So usually when you have this kind of wave shape on, then what you're showing is voltage this way, and your oscilloscope is actually always going to be showing voltage this way. But this will actually be representing current. When you put a shunt resistor in and you measure across it. Turns out that for a very simple resistor, current and voltage are related, very simply, Ohm's law. And so, if you do this deliberately and then if you put a resistor in the circuit, right at the beginning as it were, you can measure across it, and even though it's still measuring voltage, you can convert that very quickly to current. So, in other words, the current that's flowing has turned into a voltage for this thing to measure. Now, you'll still have the voltage scales and all that, and your numbers, when you make them appear, you'll get the same. They won't understand that you've turned the input to a representation of the current, but you will. Now, more sophisticated oscilloscopes actually have buttons and things that you can twiddle to put in how much resistance the shunt resistor has, and therefore automatically do the computation and give you amps, your amperage on this scale. This isn't that. This is not sophisticated enough, but the technique is essentially trivial. If I knew the exact resistance of this wire, I could use it as a shunt resistor. Just hook it in line with your battery, that is battery on one end, the thing you're trying to power on the other, then put your oscilloscope across here. It will then measure the little voltage drop from here to here, And given that you know the resistance, you can turn that into the current value quite easily. And even if you don't turn it into the current value numerically, you'll get this shape which is actually showing you the shape, the waveform of the current. Okay, so just essentially with a very well-known piece of resistance. People, of course, avoid that because it really does mean that you have to put something in. So it's one thing if you just attach it to the battery and the thing, it's pretty easy. But if you're in the middle of a complicated circuit and then you want to put a shunt resistor in, you have to actually break the circuit or open it, put it in, you know. So that's not so good. But for simple cases, you can do that. So, if they don't find you handsome, at least they'll find you handy. And keep your stick on the ice and your trigger on the screen. Now I'm wearing my Jordan Peterson shirt, so you know what that means. Yeah, clean your room, find some motivation, go out there and oscilloscope your brains out, get a move on. Wait a minute, this says duct tape, you know, like the bird. What kind of weirdo tapes up a duck? And why? And how can there be enough weirdos in the world to actually manufacture this in quantity? Oh, duct tape means it's waterproof. Oh, like water off a duck's back. Ah, that makes more sense. For a while there, I thought there was something wrong with everybody else. But if duct tape ever does fail, just keep calm and call a millwright.